Let's look at two new functions. We're going to talk about exponential function and logarithmic function because they have this relationship between them that's known as being inverses. But before we talk about that, just want to talk about these two functions and their graphs. So here, this just a cute image just kind of describing what an exponential function does. You'll see. But this is the way you write an exponential function. And what makes it an exponential function is because the variable is now in the exponent. And we have numbers under it. This is known as the base of an exponent. That's the base and that's the exponent. But a couple things to note in terms of what's going to make this an exponent is that it has to be strictly, that base has to be strictly bigger than 1. Because if it was, and it cannot be equal to 1. Because if it were equal to 1, any power you use on the number 1 is not going to change it. So that means as your x's are changing, your y's are staying the same. You'd be making a horizontal line. And you also don't want it to be negative. So the base can't be a negative number because as you choose different x values, right? Let's say, for example, a negative 2 squared versus negative 2 cubed versus negative 2 to the 4th. The answers are going to be alternating signs. So it'll be 4 and then negative 8 and then positive 16. And that's going to cause your points to be bouncing back and forth. So you won't get a nice graph. At least the graph, I mean, it's still a graph, but the graph we're talking about is those that have this behavior that I'm sort of showing in this picture. And there's two versions of it. You can either have a number strictly bigger than 1 or in between 0 and 1. But if you notice, the entire time, it can equal 0 either. Because once again, anything to the power of 0 is going to give you 0 essentially. And being equal to 1 will also just give you 1. So cannot equal 1 or 0. It can't be negative because the signs will alternate. But it can be any number other than that. So anything bigger than 0 and in between 0 and 1. So if you're looking at a number line, no 0, no negatives, no 1, but then everything else is perfectly okay. Now, knowing that this base is going to be, right, it cannot be equal to 1 or 0, knowing that, it's also not going to be able to be equal to 0. Because any number you choose, right, a 2 or a 0.5, there's no power that's going to turn your base into a 0. So in other words, the f of x will never be able to be 0. That means our y is not going to be able to equal 0. Right? That's essentially what this is saying. Let me make a quick note. This is saying that y is not going to be able to equal 0. By y, we mean f of x. And we just looked at a recent example. Remember, when y is equal to a constant, that makes a horizontal line. And it's not that we don't want it to equal 0. It just does not exist. And hopefully that reminds you a little bit of the rational function where the vertical asymptote came from any values that made your denominator 0. But some of the horizontal was because the value, that horizontal asymptote was just a value your function could not equal. Because the value of x did not exist to give you that answer. The same way here, there does not exist an x that will give you 0. And then really quick, before we graph, just a couple things to remember, right? When you raise something to the power of 0, it's equal to 1. Negative powers, remember, it can be rewritten as fractions. And then this idea we just said, right, where y is not going to be able to equal 0. Hence, that's going to create a horizontal asymptote at y equals 0. So let's graph this and see how that plays out. So once again, this cannot be equal to 0. What does that mean? We're going to have this horizontal asymptote. And remember, asymptotes are just lines that your graph gets really, really, really close to, but cannot cross them. So let's start with some quick numbers, right? So let's start, put 3, 2, 1, right? So 2 cubed is 8. 2 squared is 4. 2 to the 1 power is 2. So far, so good. I'm gonna just, to make it fit, I'm gonna add, I'm not gonna make it a perfect even scale. But at 2, or at 3, we're getting 8. So I'm gonna put that up here. At 2, we're getting 4. So let me label 1, 2, 3, 4, 5, 6, 7, 8. And this is 1, 2, 3. At 1, we're getting 2. Now, remember we just said anything to the power of 0 is 1. So at 0, we're getting 1. And we have an idea of roughly what this shape is doing. So it goes like this, right? Which is what I was trying to show here, right? This part, it has this going up sign. But remember, that x can be any number. The restrictions are not on the x, actually. There's no restriction. This x can be any number you want. Negative, positive, fraction, decimal. It just cannot, the base cannot be 1 or 0. Or negative as well. So, the base. The exponent, on the other hand, we can use -1. 2 to the -1 power, we just said, gives us 1 over 1/2. So at -1, we are getting 1/2. At -2, that would be 2 to the -2nd power would be 1 over 2 squared, which will give us 1/4. At -2, so it gets even smaller. And now this starts resembling more of that behavior around an asymptote that we've talked about. And this is the shape of an exponential function. And just like rational functions, we want to memorize this type of behavior. Because this behavior is very specific, right? It's really close to the horizontal asymptote on one end, and it grows really fast on the other. But something that we can highlight, right, is that we said anything to the power of 0 is going to be equal to 1. So we can use this. So regardless of what this base is, it can be a 2, it can be a 1/2, it can be 7. But the moment you put it to the power of 0, it's going to be equal to 1. So this point is really important. This 0, 1, because it's sort of a point where all your exponential functions, at least parent functions, are going to intersect each other. So let's do a couple examples so we can see that, right? Now, when it comes to being bigger than 1, it's always going to have this shape. It's going to have the asymptote. It's going to have that point. And then it's going to grow really fast on the right. But when it comes to being in between 0 and 1, it actually looks a little different. And we can use points to kind of show this, but for the sake of time, I'm going to show you. It actually reverses the direction. So instead of going up on the right, it grows fast on the left. So that's the difference between these. And I say that because here's that very first example of 1/3. That's a number that's between 0 and 1. But remember, even if I plug in 0 here, that's going to turn this 1/3 into 1. So I can do this using transformations. So here's my 0. Or here's my first point. And the parent function here, right? The first one I'm graphing is 1/3 to the x. It's initiating the graph. And that's going, and just like the previous one, it also has that asymptote. It has the asymptote. Sorry, let me do that again. It has the asymptote at that 0. Then it grows on the left. Now, this negative is a little different. So we've talked about having a negative outside makes a reflection on the x-axis, but a negative inside makes a reflection on the y-axis. So instead of this graph being like this, copy this. So we have one more graph to do after. The point's still in the same direction. If I'm reflecting on the y-axis, that doesn't change this point. That point's still going to be in the same place. But if I reflect it, I'm changing directions. And then this -2 means we have to shift the graph down by 2. But not only in this is the first situation you come across, not only do you have to move this point down 2, but you also have to move down your asymptote. So this point is coming down 1, 2. But the asymptote has to come down 2 as well. Because without that asymptote, I won't be able to tell where I'm approaching, right? Because the graph wants to get closer and closer to the asymptote. But if I don't move this asymptote down 2, then I don't know where to sort of draw it, right? What's restricting it? And that's this horizontal line. Let's look at another example. So a little bit bigger, or yes. Oh, I skipped this one here. So here, if you notice, the base is 3. So we're dealing with 3 to the x. So same thing as always, it cannot be equal to 0. So we have a horizontal asymptote here at 0. And then again, it has that point at 1, 0. And since it's bigger than 1, it's going to have this shape. And then, now before the quote-unquote inside either happened inside of a square root or inside of a parentheses or inside the absolute value. For an exponential function, inside is the exponent. So this +1 actually does opposite of what you think. So you think you're adding by 1, meaning you're shifting the graph to the right, but it doesn't. It actually shifts the graph 1 to the left. So it would look something like this. You move that point over, but the graph still stays the same. Nothing's changing. Keeping the graph the same. So I'm going to copy this one. Just kind of show you it's just going from here and then moving 1 to the left. That's all. Then now we have this negative outside. So now this negative actually makes a reflection on the x-axis. So it's going to shift your point down 1 to here. And then if we reflect on the x, it's going to be going downward. I'm not looking for anything perfect, but do your best. And lastly, this 2 means you have to move the graph up 2. But once again, we have to move the horizontal asymptote up 2 as well. Let me graph it. Just gonna move this graph a bit. So we see here, this point, this asymptote was on the horizontal x-axis, but then it moved up 2, and then this point also moved up 2, but right here. So our graph, the point is going to be there. Shifted 1 to the left, and it went up 2. And then we just sketch it, same shape. Again, I'm not looking for anything perfect, but just a rough sketch doesn't hurt. Here's another example. Now here it might be tricky because you're saying, wait, what do we do with this E? To make a quick note, E is approximately 2.7. Hence, that number is bigger than 1. So, but it still has a point there at 0, 1. It's gonna grow really fast on the right. And then, once again, the exponent is the inside. This -2 actually moves it to the right, not to the left. So that point's moving 2 to the right, which would be here. Luckily, moving left to right does not shift your horizontal asymptote, only when you move up and down. So here's our graph. Same shape. Once again, that negative causes a reflection on the x-axis. So that's going to move the graph down here. And lastly, that 3 moves it up. But then what else has to move? The horizontal asymptote has to move up 3. And so does that point. That point moves up 3. So it goes up 1, 2, 3, right here. Right, because this is going up 1, 2, 3. And we still have the same shape from that reflection. And there we go. That's an exponential function. Now, the relationship the exponential function has with the logarithm is that they're inverses of each other. And just to give you a quick idea of how inverses work, they have symmetry over the y equals x line, meaning that if you fold one side of the exponent, you're going to get a graph on the other side. The graph that you get on the other side is going to be the logarithmic function. So you're not folding along the y-axis, you're folding along this diagonal. And if you notice, the exponential function followed this horizontal asymptote. But if you divide that or do a reflection, that horizontal asymptote actually becomes a vertical asymptote. So instead of approaching this horizontal asymptote, it's going to approach this vertical one. And there you can sort of see how they have symmetry over that y equals x line, telling you that they're inverses. And that inverse is known as a logarithm. So here we have our exponential, right, that we did. Now, of course, this is strictly looking at when the base is bigger than 1. When the base is in between 0 and 1, it does change things a little bit. The symmetry is, we still need the symmetry over this y equals x line, but then it starts shifting and looking a little different. it starts looking like this instead. So, but we're going to mainly focus when the base is bigger than 1. Here is the exponential function, and this is the shape the logarithm is going to make. And if you notice, the horizontal asymptote is switching to become a vertical asymptote. So in other words, you're taking your x-axis and it's becoming your y-axis. And you can see that with our points, because remember this point that we're always crossing? Well, that point, just like how this x became a y, well, this x of 0 becomes y for the inverse, which is your logarithm. And look at your y is 1, that actually becomes your x. So when you're reflecting over this y equals x line, y becomes x and x becomes y. And you can see how these points are swapping between each other. There's a lot of those sort of similarities when it comes to a logarithm. But the logarithm is the very first function that you use the word log in the function. Up till now, everything has been variables and numbers and constants. But the logarithm is special. It is the first function that actually uses a word in it. And this is what the logarithm looks like. It says log base of b and the argument x. This is its notation. But because it builds from that exponential, we actually never really think about it as a logarithm. We interpret that log as an exponential and then we refer back. So it's like we're looking at the log, we refer to the exponential, and then we go back to the log. Because the log is just a word. Like most functions have had operations tied to them, like x squared. I know what square does. Absolute value of x, I know what this operation does. Square root, I know what that operation does. But what does log do? Right? It's not really a symbol. It's like sounds like a word. And the best way that we have to evaluate and work with logarithms is we actually look at it like an exponent. But a little different, because if you notice, the exponent has x as their independent variable and y as their dependent variable, which is, we still have x and y here, but when we go from our argument of the logarithm, which is the independent variable, to the dependent variable y, when you rewrite it, that independent variable y becomes the exponent of the base, and the argument becomes the output. So that switching, once again, it's the x and y's are switching in the exponential function. Because this exponential function would be written, instead of using function notation, you can use equation notation, which would be y equals b to the x. But because of this inversing that's happening, right, how that x and y are changing, so does this x become a y and this y becomes an x. And that's the form that I have written down, right? The x becomes a y and the y becomes an x. They swap between each other. And similar to the exponential, I can't have my base to be 1. I can't have my base to be bigger than 1. Sorry. I cannot have it to be 1. It has to be strictly bigger than 1. It also cannot be equal to 0. And once again, it has to be between 0 and 1. And this is just a new addition, that the logarithmic function, its argument, meaning what it gets plugged into, has to be strictly greater than 0. Because if you think about it in this exponential form, whatever values you have for your base and any values you choose for y, you're not going to be able to get 0. And you're not going to be able to get a negative number. That's why it says it's strictly greater than 0. You can get 1, because the power would be 0, and other things, but it has to be strictly bigger than 1. So here we have a logarithm. Let's try sketching it. But at first glance, you're going to notice something. Because when let me actually erase these. When I plug in 3 into the logarithm, that's going to look like this. Log base 2 of 3. I don't know the value of this. But like I said, what I can do is rewrite it into that exponential form. When the base is 2, the exponent goes here, and then the argument is 3. But if you notice here, I don't know what power of 2 will give me 3. And this is if I keep choosing my x's. Now let's not forget, in this exponential form, the one that gets rewritten, that output becomes the exponent, which this is your y. I know how to apply an exponent, but I don't know how to solve something where the variables in the exponent and these bases are not the same. They don't share any factors in common. Not saying that 3 does not exist. It does exist. It's just a number that we can't do by hand. We'd have to use a calculator to do this. So in this situation, I'm actually going to choose y values instead. I'm going to choose f of x's, not... I'm going to choose y's, not x's. So let's start with 0, 1, 2. And remember, it has to be strictly greater than 0. That doesn't mean you can't put in a half or maybe a third. Let's look. When we rewrite this, it's going to be log base 2. I don't know the x value, but it has to equal something. But I do know I can rewrite it. And that thing we're saying that it has to equal is, let me change the color, 0. And this I can rewrite as 2 to the power of 0 we know is 1. So in other words, x is equal to 1. So far, so good. This is going to be log base 2 of x equals to 1. When I rewrite this, that means 2 to the 1 power is equal to some x. Well, we know that's 2 to the 1 power is just 2. And if we keep going, right, log base 2 of x equal to 2. So 2 to the second power is equal to x, which 2 squared is 4. We have log base 2, x is equal to 1/2. Which is going to be 2 to some power which is equal to x, which this you can actually rewrite as square root of x. Sorry. Square root of 2, which is approximately 1.4. Let's see what it looks like so far with the numbers we have. So we start by saying we know that this cannot be equal to 0. But we have, that's why we get that, well, this can be equal to 0. We can't, let's go back. Our x cannot be equal to 0. And remember, when x is equal to a constant, what does it make? That vertical asymptote. Now, let's start plotting some of our points. So at 1, at x being 1, our y is 0. X is 1 and our y is 0. That's our first point right here. Again, that was the point that for the exponential was at 0, 1. This one's at 1, 0. Then we have 2 and 1. When x is 2, y is 1. And then at 4, we have 2. And then at 1/2, oh, sorry, the one at 1.5 for our x, right? Which would be 1.4. Here's 1. Here's 1. Here's 2. So that's going to be at 1.5, which would be here. Sorry, 1.4. We're going to get a half, which makes sense. It's about right there. It seems like it's following that path, right? Look, we're going here, 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 here. We're following this path. But what happens? What happens in this little piece right here? Remember, we said the restriction is on our x, but the ones we're choosing right now are our y's. There's no restriction on the y's. So instead of me trying to choose these x's here, why don't I choose y values? So instead, I'm going to choose -1. What is that going to look like? That's going to look like 2 to the -1 power, right? Or let me write it all the way out. It's going to look like log base 2 of x equals -1. And we can rewrite it as 2 to the -1 power, which is going to be 1/2. So my x is 1/2. But my y is -1. So 1, here's 1. 1/2 would be here. And this is -1. Now what would -2 look like? For the sake of time, that's going to be 2 to the -2nd power, which is going to give us 1/4. So the x is 1/4, which is here now. But our y is -2. So you can start seeing how it's getting closer and closer to that y vertical asymptote. It just keeps doing that forever. And it's what we said the logarithm would do. And again, this is very specific. This is the logarithm with base b, but when your base is bigger than 1, right? If your base was in between 0 and 1, it would look this way. The same way the exponential, when it's bigger than 1, goes up on the right. It swaps for when it's in between 0 and 1. Same thing for the logarithm. It goes up when it's bigger than 1, and then it goes down when it's in between 0 and 1. But just like the exponential, I just want to memorize this behavior. Right? This is just a property that we can use to simplify and work with logarithm. But in terms of their graph, I just need to remember this behavior. And the same, at least this is the parent function, right? And it has that 1, 0 point and this asymptote, right? But if you want to practice sort of this property that's true for logarithms, right? For a little more practice, we need to memorize this. So we know that we can rewrite a logarithm into an exponential form, which I've been constantly doing right now. Right, and let's do some of these really quick. Right, if we're trying to evaluate the logarithm, it's hard to evaluate it because I don't know what operation to do. Like you're asking me log base 2 of 16. Am I supposed to multiply 16, divide 16? Like not clear the operation. That's why we just rewrite it as your base of 2. And how it says here, the output becomes the exponent. So the dependent variable becomes the independent variable. And then the argument becomes the output. Now this is something I can understand. I know 2 to the power of 4 will give me 16. And I can just plug that back in. And if you want to posit any of these, you can just try them. I know this has to equal some value. I can rewrite it as 7 to some power is equal to 1. And we know anything to the power of 0 gives us 1. Same thing here. We need to get some dependent variable out. That's going to be 4 to some power. Has to equal 1 over 64. Which is tricky. Because we've only ever used powers to make numbers bigger. How do we make them smaller? Well, I know how to make 4 into 64, right? That would just be 4 to the power of 3. That would give me 4 to the power of 3 would give me 64. But what creates this fraction? Remember we just talked about it. You can have, well, this was for exponents, but a negative exponent makes a fraction. So I can do this by just putting a negative, and that will turn it into that 64 to go down to the denominator. Because right now it's just a positive 3. If I put a negative, it will turn this into the denominator. Here's a couple more to try. Sort of a speed round. So here it was equal to. I rewrite as 4 to some power is equal to 2. Once again, how do we make things smaller? Well, this is a very special case. This one doesn't come as obvious on how can we turn 4 into 2. You really have to recall the fact that an exponential fraction can be rewritten into a radical. That denominator is the index and that numerator is the power. So I can actually use 1/2. Because if I rewrite it, the denominator is my index. But remember, for the square root of 2, we don't write the 2 in here. And then the numerator of 1 is our power. So 4 to the 1 power. Which all I'm saying here is, what's the square root of 4? It is 2. So here's their 1/2 would be my answer there. Let's keep going. Same thing. What is it equal to? I can rewrite into exponential form. Luckily, we just did one, right? Where this could be 3, makes you 64. Once again, here's another one where what power do I need to make my base 1? We know that is 0. And then 3 to some power. We have to make it smaller. Once again, I know how to make 3 into a 9. That's just squaring it. But what makes it a fraction is the negative. And then here we go. Lastly, 2 to some power has to, 8 to some power has to give me 2. Once again, the only way I've ever seen 8 become a 2 is with a cube root of 8, which we know the index is the denominator and the power is the numerator. So it would be to the 1/3 power. And this is great practice to be able to go back and forth from a logarithm. So I'll stop it here. And on the next one, I'll do some graphs of the logarithmic function and show what does it mean that these two are inverses of each other.